Hey everyone! In this series of videos, we are going to go through some hypothesis testing and we are going to solidify the ideas that we've been talking about. And namely, we want to be able to decide which method we're supposed to use as we go through these problems. I've taken the liberty of creating a hypothesis testing and confidence intervals summary sheet that gives us the steps that we're going to follow for any hypothesis test, and then specifically how we find the p-value for large samples, small samples, and proportion parameters. And then we have steps to follow for creating any confidence interval, along with steps for finding the upper and lower boundaries for a large sample, which is the same as the population proportions, other than some of the symbols that we use. And then for both a two-tailed and a one-tailed test. And then we're also going to look at small samples for a two-tailed and one-tailed. So not only does this give you how to find P, but it also says when you're supposed to use that particular type. So as we go through these problem sets, I will reference this document and not problem sets, but as we go through these examples, I'll reference that document to help you navigate that a little bit better. So let's start with example 1 here. We have an automotive battery manufacturer guarantees that the mean reserve capacity of a certain battery is greater than 1.5 hours. To test this claim, you randomly select a sample of 50 batteries and find the mean reserve capacity to be 1.55 hours with a standard deviation of 0.32 hour. At a 0.10 significance level, do we have enough evidence to support the manufacturer's claim? So let's just start with that part, and then we're going to verify by constructing a confidence interval. Notice the confidence interval matches up with the significance level. 90% confidence means 10% is left in the tails. So you'll notice the bold 50 here. The sample is 50. We were given a mean and a standard deviation, which means we are talking about hypothesis testing for the mean for large samples. When the sample size is 30 or larger, that is a large sample. So these are the steps we're going to go through that we've been doing for a while now. First, we're going to establish a null and alternative hypothesis. Then we're going to find the p-value, which is what you use these subsections for. And then we're going to compare the p-value to alpha, which is our level of significance. And then we will write a sentence about the decision that we made in step 3, whether to reject or accept, not accept, but fail to reject our null hypothesis. All right, so let's go ahead and establish a null and alternative hypothesis. So I'm seeing the words greater than here. And so my null hypothesis, H sub 0, is always going to be the baseline here. So in this case, 1.5 hours for the battery capacity. My alternative hypothesis here, since it says greater than, is that mu is greater than 1.5 hours. And so what we're doing here is we're trying to see if the sample that we got is statistically significantly larger than 1.5. And how we do that is we find the probability that we would randomly select a sample that has this mean and standard deviation. And if that probability is small enough, in this case smaller than 0.10, then we have enough evidence to say, hey, maybe this they're onto something here. So let's look at the steps here to find the p-value, because I want to know what the probability of getting this value is. Okay, the probability, first I have to identify the mean of the sample if given, or calculate it using the average function. So that would only happen, I'd only have to calculate it if I were given data values instead of just given what the mean is. So in this case, we have the mean. This is x bar, the sample mean, and that's 1.55. We have to identify mu, which is the thing in our null hypothesis. So this is our assumed population mean of 1.5. And then we have to find the standard error. In order to calculate the standard error, we have to identify the standard deviation. So it's either given, S is either given, or I have to calculate it using given data. Again, I'm not given any data here. I'm given the statistics on the data. This is the standard deviation. So the standard error is going to be the standard deviation, 0.32, divided by the square root of n, which is 50. And that's all spelled out here. Calculate the standard error, and then it tells you what the formula is for standard error right over here. So now, because this is a large sample, we can assume that it's normal. And so to calculate the probability that x bar is greater than 1.55, I always use the sample mean x bar. So the probability that x bar is greater than 1.55 is going to be 1 minus norm.dist. I'm going to have to go ahead and do this in a different cell so it actually calculates. So I'm going to do 1 minus norm.dist, and that's going to be x bar mu comma standard error comma true. And again, this is all spelled out right here. If x bar is greater than mu, we're going to find the probability that x is greater than x bar, and that's 1 minus the norm dist. It's all right there. And so that comes out to 0.1346. Since this is larger than the 0.1 of our significance level, then I must fail to reject the null hypothesis. And that is spelled out right up here, because this is the same regardless of what type of test we're doing. If the p-value is greater than alpha, we're going to fail to reject the null hypothesis. I didn't put anything in here in the cheat sheet about type 1 or type 2 errors. It seems like everybody's been following that pretty easily. So I didn't put anything in there about that. So I failed to reject. Now I'm going to write this in a sentence. There is not enough evidence to support the claim that these batteries last longer than 1.5 hours. There's just not enough evidence. And there's not enough evidence particularly at the 0.1 significance level. So if we had increased our significance level to 0.15, then this would be enough evidence. But it's unethical to pick your significance level after the fact, after you know what your p-value is. All right, so now we're going to verify these findings by constructing a 90% confidence interval. Now remember, this is a one-tailed test because we're just doing greater than. And it says right here, if we're just doing greater than and we're looking for the confidence interval, if we're just doing the probability that mu, or if we're just doing that mu is greater than a number, we're only going to find the lower bound here. We only care about the lower bound. So that means all 10% that's left over in our confidence interval is going to be the bottom 10% of our curve. And when we think about the normal curve, so this spells that out right here. So the lower tail, if it's one-tailed, the lower tail is always just alpha. So for a 10% confidence interval, that leaves, or for a 90% confidence interval, that leaves 10% below. And as a decimal, 10% is 0.1. That's the area below the top end of my lower tail. And that's what this is talking about here. It says we have to identify the proportion under the normal curve below the end of the lower tail or below the start of the upper tail. So we just want the end of our lower tail here going from left to right. And so what we need to identify is x bar. That's the middle of my x bar becomes the mean that I use for my confidence interval. I need to know the proportion or the area under the curve. In this case, that's going to be 0.1. And then I also need to know the standard error. This is something that does not change from this part to the previous, so I'm just going to reference this value over here. And so to find the lower bound, all I need to do is use my inverse norm function. It says right here, if I'm going to find a one-tailed test and I want to find the lower bound, then I'm going to do norm inverse alpha x bar standard error. So my lower bound is going to be norm dot inverse and then proportion comma x bar comma standard error. The mistake that people have been making is putting the mu here for x bar, but we're using the sample to construct the confidence interval, and we're trying to see if mu is inside that confidence interval. If it is, then we're going to fail to reject the null hypothesis. If the population mean doesn't make it in the confidence interval for our sample, then we reject the null hypothesis. So in this case, notice that my lower bound is 1.492. So anything above 1.492 is contained in the confidence interval. And since 1.5 is one such number that is above 1.492, then we would also fail to reject the null hypothesis because mu is in our confidence interval. So that just confirms the fact that I should fail to reject the null hypothesis.